In this video, we now come to one of the main constructions in this chapter, which are blowups. So the idea there is you're given X, any variety, and you describe a particular birational map from X tilde to X. We will construct these, and our plan is first, we start with the case when X is an affine variety, and then we construct these birational maps called blowups, and they depend on some input data. The input data that we give is, for example, that we specify some functions on X in particular. This will then lead to the blowup of the vanishing locus of these functions. So first we say when X is affine, what does it mean to blow up this closed subvariety of X? And then because these constructions are kind of nice and independent of the exact choices of these functions, these can then be glued, and then we upgrade from the case of an affine variety to an arbitrary variety. And what does it mean to blow up some closed subvariety? But so this is just a big plan, and we start very modest in this affine setting. So this is the next construction. And there we say if X is an affine variety and f1 up to fr are an A of X, and some functions, then, well, first of all, we can look at U, the open subset, where not all of these functions vanish simultaneously. And then on this U, we claim that we have a morphism from U to the projective space PR-1, which sends X to, well, this vector where you record these R functions, but now you see it as an element of the projective space PR-1. And so we can check very easily that this is a well-defined map, right? Because since we're away from this locus where all of them vanish, this gives a well-defined point in this projective space. And what you should check for yourself is that this is not just a set-theoretic function, but actually, again, it's a morphism. So we have seen something like this in the setting when this here was a projective variety and we removed the vanishing locus. But I mean, you can go through the same proof and just check that everything works, or you can try to reduce that proof to this case here. But in any case, it's possible to check that this is a morphism of algebraic varieties. And so then we observe that, well, given any morphism, we can always write down the graph of the morphism, right? The definition is just it sits in the product of the domain and the target of the morphism, and it's just this set of pairs x, comma, f of x. So this is always true. What is nice here is that since the target is a variety, so since it's separated, we have seen that this implies that this graph is actually a closed subvariety of this product. So this is nice. And then we have a second inclusion because remember, U is an open subset of X. And so U cross PR-1 is an open subset of X cross PR-1. So we have this composition, first a closed embedding and then an open embedding like this. And now we come to the definition that we're interested in. We define the blowup X tilde of X at these functions f1 up to fr by just taking this subset here, gamma f, we see it all the way here as a subset of X cross PR-1. And there it would only be locally closed. And so what we do is we just take the closure in this big ambient space. So this gives us, of course, a closed subvariety here. And then note that, of course, this here has a morphism to X, which just projects to the first vector. And so we call the restriction pi of this projection map to this closed subvariety. We call it, again, pi. And so then this X tilde maps to X. And this is the blowup. So Gartman in his script always just uses this notation X tilde. Sometimes I find it more convenient to record in the notation which functions you blew up, and then I use this notation. Okay, so this was already the definition. And you see, this is kind of a very abstract definition. We just say, take the subset, take the closure. We're going to see better ways to describe what exactly we get here with concrete functions and so on. For now, let's just see if we can draw some conclusions from this definition. So the first is that when we're still at this stage, we just look at the graph gamma f inside u cross PR minus 1. Then we can, of course, always restrict this projection to this subset gamma f, and then it lands in U. And it's always the case, if you think about graphs, it's always the case that if you project from the graph to the first factor, to the domain, then you get an isomorphism. The inverse is the map which sends x to the pair x comma f of x. So we know that on this open set U, the graph is still just an isomorphic copy of U. And then the claim is that inside, so if you take this closure, you get x tilde, then because this graph here is still closed inside this open set, the closure doesn't add anything. So what I'm saying here is, it's a purely topological claim that taking the closure inside here and then intersecting again with U cross PR minus 1 just gives you back gamma f. This uses one of these exercises that we had on an exercise sheet that said since this is closed, the closure doesn't add anything inside U. And so this means for this projection map pi from x tilde to x, if you take the pre-image of U under there, then you exactly get gamma f inside here. And we know gamma f is isomorphic to U. So this shows that inside the x tilde, we have this copy of U sitting in there as an open subset. And that's very nice because then if we restrict to the case, so a priori x was allowed to be any affine variety, but if x happens to be irreducible and the fi are not all 0 in this ring, then U is non-empty because there's at least one point where not all of the functions vanish. So we have this non-empty open subset in there. It's then automatically dense. And then we see that, or the claim is then that the x tilde is also irreducible, right? Because the gamma f is isomorphic to U. U as a dense open subset of an irreducible space is also irreducible. And then we had this exercise which says that if you have this irreducible set gamma f and you take the closure, it's still irreducible. So this shows that because x was irreducible, also the x tilde is irreducible. So we have a map of irreducible varieties, and we have that U sits inside here and U also sits inside the other one. And so this shows that this map pi is actually a birational map. So we see that we got towards our goal. The blow-up is indeed an example of a birational map. And then one final piece of notation is, so we talked about U a lot, but then another interesting locus is what is the complement of U inside x tilde? This sometimes is called E, and it's called the exceptional set of the blow-up. So this is a set where this map pi possibly is not an isomorphism, but it could do something interesting there. And some more bits of notation. So if you have y inside x, some closed subvariety, then we had as input data these functions f1 up to fr on x. And so via restriction, you also get functions f1 up to fr in a of y. We just use the same notation here. And then, well, y is still an affine variety, so you can still take the blow up of y now at these functions. You can also call it y tilde. by definition, it sits inside y cross PR minus 1. And since y is closed in X, this sits inside X cross PR minus 1. So we see that y tilde automatically is first of all closed in here. And then, well, because everything is closed, you can check that the closure, which is used to define this y tilde, automatically gives you something in this closure, which is used to define the X tilde. And so this means this blow-up y tilde always sits as a closed subvariety of the blow-up X tilde. And to show this, you use that y tilde is the closure of this set here, and so it's automatically sitting inside the X tilde. Okay, and as notation, this y tilde is then called the strict transform of y inside X tilde. So for now, this is all pretty theoretical, but we're going to see examples of all of this in the next video. Just one final thing to mention is that if X has some irreducible decomposition from, so as a union of X1 up to Xm, then, I mean, all of these Xi are closed subvarieties of X. And the claim then is that if you take X tilde, the blow-up, and then take its irreducible decomposition, then you exactly get these kind of strict transforms X1 tilde up to Xm tilde. So the irreducible components of the blow-up are just the blow-ups of the irreducible components of the original space. Okay, so this was the theoretical discussion, and then next video we're going to see some examples and get our hands dirty.